Consider this object that you see on the page. It looks like a toilet paper roll. Now it's going to be dense inside except for an interior hollow tube like a toilet paper roll. Now this particular object can be constructed in a couple of different ways. Number one, we could take a bunch of washers and stack them together. Now each one of these washers has the same size hole cut out of it, so that when we stack them, it creates this hollow tube in the middle, like you see here. Then another way to construct the toilet paper roll would be using sheets or shells. So we'd have a smaller pink shell followed by a blue shell and a yellow shell and a green shell, and we would stack those shells together or wrap those shells around one another to create the object as well. If we look at the shells individually, some of them have less length than the other, so the pink shell needs to be smaller because it's the interior wraparound, and then we have the blue and the yellow will be wrapped around and the green will be wrapped around. These shells will create the same exact toilet paper roll look. See? So these stacked together make this toilet paper roll. These wrapped around one another make the same toilet paper roll. Now each one of these shapes here is a washer, and they have itty bitty thickness to them. So like a poker chip, each one of them has a real thin thickness. But that is very different than the shapes over here. Here we could say each shell has a thickness. So if I I'll draw it like this, like here's the blue, but it has a little bit of thickness to it. So very thin piece of paper, but even the paper or toilet paper would have some thickness to it. So each one of these shells has thickness. Now suppose you had a choice of which kind of toilet paper you would want. Sheets that are designed with washers or sheets that are designed with shells. I certainly hope you would pick the shells, because I personally would not like to wipe with these washers for obvious reasons. Consider the area bounded between the graphs of f of x and g of x from x equals a to x equals b, as seen here. Now, inside this region, the only rectangles that make sense are ones with vertical orientation. You see, no matter where I draw a vertical rectangle in the shaded region, the top will be the pink f of x and the bottom will be the blue g of x. Horizontal rectangles won't work in this region because, as you see here, the top and the bottom of the horizontal rectangle is the function itself, f and g. So here the top is g and the bottom is g. Horizontal rectangles will not work in this region. Now we've learned previously that if we took this shaded region and revolved it around a horizontal line, let's say y equals k, then we would take the rectangle and rotate the rectangle about the horizontal line. So let's draw that. This is a review from earlier. And when I rotate it, it's a little sloppy, but when I rotate it, you see I have half of the washer that would be created. And that washer would look something like this, and it would have a hole in the middle. But that's taking a vertical rectangle and rotating it vertically to create the washer. Now in this lesson, what if we want to take the shaded region and rotate it about the line here, x equals k? I hope that you see that the shape that we're dealing with now is no longer a washer. See, if I take this rectangle here and I rotate it, then I have to take a similar rectangle over here and draw, and then I have to take the tops and wrap it around like this, take the bottom and wrap it around like that. So I do not have a washer, I do have a cylindrical shell. In this case, I took a vertical rectangle, but I rotated it horizontally. So what we're going to learn in this particular lesson is that the rectangle we draw is not dictated by the direction of rotation, but is dictated by the region itself. See, again, no matter what, before I learned of rotation, I knew I had to have a vertical rectangle. So then the question becomes, do I rotate vertical rectangle vertically, which is a term I like to say with the grain. So vertical rectangle rotated vertically will be with the grain, which will lead to a washer. But if I take a vertical rectangle and I rotate it horizontally, that is what I like to call against the grain, in which case we will have cylindrical shells. If we take a look at the bounded region between x equals f of y and x equals h of y, without knowing which way we're going to rotate, we can determine from this shaded region the orientation of any rectangle. And I hope you can see that the orientation would be horizontal. Again, the top of the rectangle or rightmost point is always x, and the left or bottom is always h of y. So f of y on top, h of y on the bottom. And that's anywhere we would draw this. So that's predetermined. Now, if I'm going to rotate this around the line or about the line, y equals k, I would take these rectangles that are horizontal and rotate them vertically, creating the shell. However, if I were to take each one of these rectangles or the entire region and rotate it about x equals k, well, then that's the traditional with the grain, creating the washer. Do you see the fundamental difference between these two? This is a flat, skinny poker chip, and the blue is a thin piece of paper being wrapped. Completely two different sheets, like the toilet paper example. Picking one sheet over the other, they have different geometric properties. We next want to come up with a formula for the volume of a cylindrical shell. Let's draw a set of axes, and then let's draw a rectangle. Let's draw a vertical rectangle, and let's rotate that vertical rectangle against the grain to create a cylindrical shell. Okay, so let's take a look at this. Suppose I took this shell, trimmed it, cut it, and then unwrapped it. Well, I did that. It would be longer like this. Okay, not very neat, but that would be like a rectangle. Keep in mind that this has a little bit of thickness. See that? Okay, let's make a little bit of thickness here. There we go. So the question becomes, what is the volume of this rectangular box, if you will? Well, if we call this the height, if we call this the length, and we call this the thickness, this little, not doing yellow here, this little sliver there as the thickness, then the equation for the volume of that is clearly going to be length times height times the thickness. But what I'd like to show you is this length here is actually this length here. See, I took the one sheet of paper, cut it, and then spread it open. So the length we see here is the same length we see here, which you should recognize as the circumference, which is 2 pi radius. So let's update our formula. The volume of a cylindrical shell is going to be 2 pi radius times the height times the thickness. in this particular diagram, this distance from here out to the edge is the radius, and that's synonymous with the x value associated with that particular rectangle. In fact, you could say that the rectangle has the first side and the second side, and essentially we say that x is the average of those two sides. So in this case, the radius is x. Now consider the graph of f of x bounded with the x-axis between the x values x equals a and x equals b. In part A, we want to take that region and rotate about the y-axis, or x equals 0. We're going to first draw the rectangle that makes sense, and that must be a vertical rectangle. Then we're going to express the volume of it. So the volume equals, from the first rectangle will occur at A, and the last rectangle will occur at B. So from A to B of the circumference length, so that's going to be 2 pi whatever the radius is. Alright, so let's see if we can't look at that. Here's going to be the curve on the other side that gets rotated, and no matter where I draw the rectangle, the radius is going to equal the distance from the y-axis out to that particular rectangle, which you can see anything from 0 to an x value is the quantity x. So the radius in this case will be x. Now the height of every rectangle is simply the f of x. That would be this rectangle's height from the function to 0, the x-axis. And of course, the thickness would be dx. In the second illustration, we're going to take the same region bounded by f and the x-axis from A to B, and we're going to revolve it around some line x equals k. So let's draw that x equals k. X equals k. Alright, so now when I take this rectangle and rotate it, boy, that's going to come way out over here. That's supposed to be a rectangle. Pardon me for its ugliness. And then we have this big long circumference. Okay, so we're about to set up the volume. Volume equals, again, from the first rectangle at A to the last rectangle at B. From A to B, from x equals A to x equals B. Now we need the circumference, which is 2 pi, and then the trick is to determine the radius. That's really the biggest part we have to do here. And so the radius is going to go from here to the axis of revolution. That's our radius. And that's not the distance of x. The distance of x is this distance here. That's the distance of x. So how would we express the radius, the distance from here out to the rectangle? Hopefully you would see that is the distance k minus x. See that? This value minus this value. K minus x is the radius. Now what is the height of the function? Well, that's clearly the height of the rectangle, which is f of x. And then we cannot forget the thickness, dx. In our final illustration, part C, we're going to rotate the same exact region about another vertical line. This time the vertical line is going to be x equals v, but it's going to fall to the left. X equals v. Alright, again, I don't always draw these, but for this case, oh man, it looks like we might have to scroll over here a little bit to get that in. Alright, looks like this. So one of those guys would rotate like that against the grain, creating this cylindrical shell. This time my radius is from rectangle to axis of revolution. There's my radius. And then the key to the problem is determining how to express that radius. So I'll scooch over here and say our volume equals the integral from first rectangle to last, a to b, the circumference, which is 2 pi. We're ready for our radius, which is this case going to be the x value minus the v. This x value minus this x value to create the distance or the radius. Our function is f of x, height of the rectangle, and our thickness. In example 1, we're looking at the bounded region between these two curves, and before we do any revolving, let's draw rectangles that make sense. So, like we showed in the warm-up, the rectangles here that make sense are going to be the vertical rectangles there. Now, let's take a look at part A. Part A wants to revolve this shaded region about the line y equals 9. So here we go, y equals 9. So if I take that rectangle and rotate it about that line, I'm taking a vertical rectangle and rotating it vertically. It looks like I am rotating with the grain. Can you determine the shape that makes if I rotate? I'll try to come up here. I got cut off a little bit, but can you see that shape that's being made? That is not a shell, but a washer, and this should be review for you. So now, the volume equals from the first rectangle, which is going to occur at x equals 0, to the last rectangle, which occurs at 5. And you can verify by plugging 5 into each one of those equations, and they will both yield 0. And so this is traditional washers, which is pi, and then the outer radius is going to be the distance from here to here. So that's going to be, let's get white here, that's going to be 9 minus the sine function, so it's going to become plus sine of pi x over 5. That is the outer radius, and the outer radius has to get squared. Then I'm going to subtract the inner radius, and the inner radius is going to be the 9 minus the parabola 5x minus x squared, and that whole thing is the inner radius, which has to get squared, and there we have it. Pi outer radius squared minus inner radius squared, and then the thickness of the washers dx. In part B, we're going to take the region and revolve it around the y-axis, or x equals 0. So we're taking a vertical rectangle and ultimately going to revolve that against the grain. Okay, so let's get ready to set this up. So our volume is going to be from the first rectangle at 0 to the last rectangle at 5, but this time it's 2 pi radius. So do you see it here, the radius? Radius is going to be from the axis of revolution to the rectangle itself, and that's simply the value of x. Now we need the height of the particular rectangle, and that height is going to be top minus bottom, top minus bottom. So that's going to be the difference of the two functions to give us the height of the rectangle. So it's going to be the parabola minus the sine function, but minus the minus becomes plus. Okay, the brackets represent the height of the rectangle, and then the thickness dx. Part C, we're going to rotate the region about x equals 6. X equals 6 is out here like this. So to do that, we're going to take a vertical rectangle, rotate it horizontal. We're rotating against the grain, the opposite of its orientation. All right, here we go. Let's set up. Volume equals 0 to 5, 2 pi radius, and our radius is going to be the difference between these two values. So that's going to be 6 minus x, and then the height of the rectangle again is the difference between the two curves. Parabola minus the sine function. No squared, it's just the height of that rectangle and then the thickness. In part D, final part, we're going to rotate about x equals -1, so the volume is going to equal from 0 to 5. Each one of these rectangles will become a sheet or a shell. 2 pi radius times the height, and the height is the same as it was in the prior two examples, a minus. Okay, so let's just get this out of the way, and times the thickness. And for the good old-fashioned radius, this is the radius here. The rectangle will rotate over the axis of revolution. This distance from here to here is x, but then we have an additional distance here. So we will say x minus a -1, which becomes +1 for the radius of each shell. In example 2, we have to draw horizontal rectangles. Those are the only ones that will work. In part A, we're revolving the rectangle about the line x equals -1, and it looks like that is going to be with the grain. See, we have horizontal and we rotate horizontal. That's going to be with the grain. That's going to be washers. So volume equals from the first rectangle, which occurs at y equals 1, to the last rectangle, which occurs at y equals 3. This time it's pi. And now we need outer radius. Now the outer radius is a big mess. It's 2y minus 1 cubed minus y minus 1 to the power of 4 minus a -1, so +1. That whole thing is the entire outer radius, and I have to square it. And then I have to subtract the inner radius, which is going to be 0 minus -1, or simply 1 squared. This is the review type. Pi outer radius squared minus inner radius squared, and then the thickness. In B, we're going to rotate the region about the x-axis, so volume equals, I hope you see now, this is against the grain. We have a horizontal rectangle being rotated vertically, and so it's going to be from y equals 1 to y equals 3, 2 pi radius, and our radius is going to be the value of y. And then the height of that rectangle, now the rectangle is on its side, but the height of the rectangle is the function itself, 2y minus 1 cubed minus y minus 1 to the 4th. That whole thing is the height of the rectangle, and then the thickness of each of those rectangles is dy. Part C, we're going to rotate about y equals 4 against the grain. Volume equals from y equals 1 to y equals 3. The circumference 2 pi. Radius in this case is going to be 4 minus y. The height is still the same. That's 2y minus 1 cubed minus y minus 1 to the 4th. And then the thickness dy. In part D, we're going to rotate about y equals -1. So the volume is the integral from y equals 1 to 3, 2 pi radius. Let's take a look at that. The radius is going to be the value of y minus -1, so y plus 1, and then the function itself, which we've written a couple times now, y minus 1 to the power of 3 minus y minus 1 to the power of 4, thickness dy.